Good morning. I'm Eric Liu from Samsung Electronics. I'm in charge of DVS sensor development and application development in the Samsung system side. Okay, this is our light. I will introduce our system side DVS sensor hardware. Then I will cover some of the application we made internally. Then summary and discussion will be followed. We made several versions of the DVS chip. Actually, we started it from 2012. We made a 9 micrometer DVS chip at the time. It's collaborate with Toby Delbrook, and the resolution was 120 by 8 by 128. Then we moved to increase the spatial resolution to the VGA, and it was the first result. And at that time, the dynamic range was just 66 dB. But the importance of this chip was that we made a 9 micrometer BSI pixel. But actually, the power consumption and interface, everything was pretty big, and we have to improve much more higher to get the better performance. Then this is made with we call it generation 2, and the main focus was we need to increase the data bandwidth. It's up to carry out the 300 mega events per second. The main reason is when DVS moves and when the object moves, actually the data generation of the sensor was very high. When it was 128 by 128, it does not matter. But when it becomes a VGA, actually the main drawback of the event camera was the limitation of the bandwidth handling of the data to be received by processor. So the focus was the increase of the event rate, transfer rate, and then we put all the digital logics and the interfaces. Then we made that it's around 80 milliwatt of the power consumption. This is the commercial version of our DVS Gen 3, and there was the main change was that we changed the AER to be a scanning mechanism, and we introduced the global hold and global reset, and these things are introduced. Actually, I will summarize why we shifted to this technology. Then internally, we have a DVS Gen 4. This is a 1.2 megapixel version, and we reduced the pixel size and 4.95 micrometer. And we have the frame rate. It's more than 1,000 frames per second, and the minimum detectable contrast is now we achieved around 27% when we guarantee 99.9% of response made by the pixel. Actually, this is our first meaningful result when we made the chip. It's a DVS Gen 2, and it looks nice, and we could get some reasonable image quality with our 9 micron pixel. But actually, this image is showing some best case. But when the data rates increase, actually event generates more, then there was lots of motion artifact, and also latency increased, and it was difficult to reconstruct of some fine etch image from the DVS. So the main reason was that actually, as you can see, the DVS, the data generation from the sensor is actually it depends on what we are trying to observe, and when the object is moving fast or the contrast is high, then the data traffic is become abruptly increased. And also there is another difficulty of design the DVS is that the delay of the events from the pixel to outside it depends on the illumination condition. Also, it's even in the pixel side, if the illumination is not good enough, the log amplifier delay of it has some serious delay of the current generation to be trigger the event sensing circuitry. So combine all the things, then actually what we observed from the generation 2 is that this situation. So there is with the when this is we observed the flickering LED light. It's illuminating on a wall, and conventional we modified AER to increase the bandwidth. And with that technology, it's actually it select the column when the first events come out. Then actually it search the neighborhood columns. Then it's start to sending out all the column data to the right side. But as a result, when we reconstruct the full scene, then you can see there is some AER-induced image artifact is made. Our best case is that when it's one event generated in one instance, then we have to get this at least this fine object scene is better to track some object or recognize some object. So the basic approach what we analyze from the Gen 2, Gen 3 is that removing AER to the simple scanning mechanism. The basic AER has a negotiation process when there is event data is generated in a pixel. Then each pixel have to negotiate with arbiter outside. Actually, this is increasing of the delay of when actually to sending out the actual data to the outside. When the pixel array is small enough, like 100 by 100, this is good enough. But when it becomes like 300,000 pixel and 1 megapixel, then actually this generates a lot of latency. It's not because of the illumination, but because of this AER, the output of DVS scene becomes very blurry and slow down. So it's difficult to get the fast updates of the scene. So we, after some series of study and making several different chips, actually we find out for some best readout architecture for our DVS sensor. So the basic first thing was that we shift the AER scheme to the column scanner, and also we introduced some kind of global shot mechanism in the pixel side. So okay. So as you can see, the actual pixel delay of event delay is become very low when we use the conventional AER. So this is the number of events, the generation is so when it's less than 10 mega events per second, if it is generated, then the timestamp error become much lower, less than 1 microsecond. But actually, when it is more than 100 of mega events generated, then the time delay is become more serious. Another problem is that because of this AER, column AER, it's the artificial edges was created, and we have to put lots of software work to reshape the artifact object to be clean, to make it clean. And this is what we get by introducing the global hold or global shutter operation. So in a Samsung DVS, we put a global hold scheme by putting 2 capacitor memory on the pixel. So with some trigger signal or with the promised the time, we can freeze all the events to get all the events at the same time. If somebody know about the DVS pixel operation, Actually, it's difficult to freeze all the events at the same time because it can roast of the events when there are delay of the reading the events from the pixel. So we put this global hold memory mechanism and the shutter mechanism in the pixel. And another circuitry we put in the pixel is that we put a circuitry to clean out the ghost events. So DVS log amplifier has a slow response characteristic. So when the illumination condition is dark, then the event is continuously generated and it gives more events outputs from the sensor. So when you move the DVS sensor in a dark room, then you can see the tail events come out from the sensor. So what we put it in the sensor is that we have a circuitry to reset all these slow bearing currents events not to be sent out from the sensor. And in our system-less DVS, we put an anti-flicker filter is embedded in as a hardware. Actually, this is not in a Gen 3 commercial version, but in a Gen 3 half VJ version and Gen 4 DVS. And this is the example. It's a C. There is a background. There are flickering monitor, but we can remove. And this is the corridor with the flickering lights, but we can still get the non-flickering events we can receive well. We can filter out. So this is the case of the when there are flickering events, but this is about the possibility of a flickering event versus a real event. So we can get around the 97% of the true events we can get from the sensor. And another thing is that we made some low power operation mode by putting the histogram counting of 32 by 32 group of pixels, and we made a very low power counting logic inside. Then by combining this, by looking this histogram change, we can make it as we can create a triggering signal to wake up the outside processor. So this DVS only operating with only minimum power, and we turn off all the other output interface except the triggering interrupt pin. Then this can be used for the low power IoT applications. This is one commercial application will come out soon. It's about the human detection. So we spent more than 8 years to create some meaningful application in a commercially acceptable. That means that low power and low processing power, and also the full constructing cost should be something like less than $100. Including all the processor and sensor and modules and everything. And this is the first example. Actually, this is a quite simple example. It's detecting of events, and by looking at, we classify whether it's a human or not. So, as you know, the DVS output is only has edge images. But Davide showed that he can reconstruct the actual grayscale. But we use this edge images to training the events as a way to make some classifier for the human. So we labeled more than 1 million of VJ data, and we made a neural network. And there are around 11 categories like a person, dog, cat, and we train it. And we made some full process from the event sensor to the triggering of some action from that devices. So basically, it's we use a neural net, and this event processing is combined with it's a collecting of the events and the reconstruct and finding of region where we have to focus. So we have to refine of the full architecture to be processed in a small application processor. So this is the result. It's the human detection accuracy for the around 10 lux. It's more than 98%, and actually false alarm rate is it's less than 1%. So this is the example. It's yeah, there is a dog. I don't know whether you can see dog and the human, and here it's we train it with whether it can give a false alarm. There is a robot vacuum cleaner and the fans and everything. There are some other moving objects, but we could keep the false alarm rate in less than 1%. So the lesson from this small network with the DVS image is that for us is that the sparsity and the binary feature of DVS was good enough to making a human classification network, and even with this edge image, we can making a very high accuracy. Even compared with the CIS grayscale image, we get better classification accuracy. And the main reason we try to understand why it give a better accuracy is that actually in a RGB or grayscale image case is that the neural net have to process even the background information, but DVS case is only dealing with the edge information. Actually, that give a extra benefit to get a higher accuracy. And another benefit, it's when we use the same resolution of the CIS image, then it was the processing flops was it's 5.8 gigaflops, but when we use the DVS, it was 81 megaflops. And also number of layer can be reduced from the 91 to 24, and the processing time also was 15 milliseconds. So actually this is now we're running on a Exynos in a 1.4 gigahertz process, and we can now handle around more than 50 frames per second, including receiving DVS signal and running the full neural network to classify human detection. And this is about the DVS SLAM. This another example what we are trying to make internal is that DVS space. I think you probably well know about what the SLAM is, and we actually follow with some existing SLAM algorithms, and we are trying to use this events data to get a high accuracy SLAM result. This is our SLAM architecture. It's we get the DVS events and also IMU data, then make it's converted DVS signal as the grayscale image, and the IMU also information also used. So there are some different updating speed, like DVS framer is like 10 milliseconds, every 10 milliseconds we update. Then finally there are some different updated speeds of the different blocks. Then finally what we get is around 100 hertz of 6 DOF pose data result we can achieve. So this is the okay. Oops. Yes. This is the demonstration. We made in ISCC in last February, and we achieved its update speed was that 10 milliseconds, around 10 milliseconds, and we could use the 1000 frame seconds of the event update rates. So let me show some comparison between CIS-based approach and the DVS-based approach. Actually, this is the commercially available CIS SLAM, and this DVS SLAM is we made it internally, and we compared the position error and the other drift error, and we compare the performance. But actually, I think this is not very fair because the CIS-based solution lost its position at some moment. As you can see here, it's at some moment when we shake our sensor SLAM devices with a high speed, and when the illumination condition is it's become dark, then the CIS lost its track position easily. So after that, it was difficult to measure its position. So when it started the drift, actually it was difficult to compare the performance in between. But actually, when it is not drifted, the CIS SLAM also gave a very good positioning error. So from this result, what we are and with some difficulty to improve the DVS-based SLAM accuracy, actually one of the conclusions internally what we are making is that we feel that we need to combine these two solutions together. Okay, and this is we are making some DVS plus a CIS SLAM, and actually we made our own internal modification of this hybrid SLAM algorithm, and now we have a slightly better the accuracy, like around 10% or 20% of improvement we made. And this is some internal feedback to the hardware team, what the best DVS it should be we can make. So thinking about how to combine this DVS and the existing CIS, how to synchronize and operate of different vision sensors and integration of the IMU sensors. So these are all our new tasks to do. Okay, this is my summary of talk, and we changed several design parameters like AER, and we introduced a frame concept, and it mainly to reduce the latency and motion artifact. And as a result, we could achieve the low power operation, low power consumption, and small pixel size operation. Actually, these things are we achieved. And one example of the benefit of DVS is that the visual recognition, it's even with a smaller neural network, we could achieve the higher accuracy. So the first application what we are making was a target object was human, but extending of this object class is not some difficult one. So if you will want to making a low power and high accuracy, then DVS can be one of the good sensor for this classification application. And we are doing a DVS SLAM, but DVS and CIS have different features. And DVS is good to making a robust tracking, and CIS can give a better position accuracy. So combination of these two sensors could be, I believe it can be the best SLAM we can achieve with the combination of these two. And there are still many design issues from my side. It's actually bandwidth is one of the big hurdle to maintaining the latency when the spatial resolution is become larger, like 1.2 megapixel. Actually, we could we cannot handle this 1.2 megapixel, this R&D version, because we made 10 gigabps of interface from this generation 4. But even with that, when we moving the DVS sensor with the high speed, then the event generation from the sensor is become very huge. So it's quite difficult to manage these events. And another thing is that the pixel sensitivity in a dark illumination is also another hurdle, because its response time is become longer. It's difficult to maintain the clean object edges. So we need to improve it in a circuit level. And then it's a high level or the hybrid combination of a sensor or in a processing way of the events data properly. These are all the innovation research should be followed to get all the benefit from the event sensor. Thank you. Was my question.